Hello, my name is Campbell Lachlan and I'm going to tell you how protons work and interact with other nucleons and how this can be used to benefit mankind. From my previous video titled What is an Electron? We saw that science is wrong saying that an electron has no structure because an electron is a moving point charge with an electrostatic and complex electromagnetic field surrounding it. We call this dedicated field its L field, or L for short. Charge, electrostatic field, complex electromagnetic field, its L field. Both electrons and protons are charges with their accompanying L's, and they originate from and are fed by the source. Remember that the proton's L is 1836 times the magnitude of that of the electron, so the electron's acceleration, being a function of time, is 1836 squared times that of the proton, given the same input. This is why the electron is the primary photon emitter, but the proton and its L is equally important for other reasons. It's well proven that a charge accelerating quickly will emit photons. The greater the acceleration, the greater the quantity of photons. Proton Ls also have the property of attraction. In a steady state environment, proton Ls attract in nuclei between nucleons at approximately 10 to the minus 15 of a metre, and between molecules at approximately 10 to the minus 10 of a metre. This L attraction is significantly stronger at these specific separations than the repelling Coulomb forces and is the main reason for the molecular, thus dimensional stability we observe in stable forms of so-called solid matter. Consider that molecules, which are in minor but relative motion, share valence electrons which normally orbit at some 10 to the 15 Hertz, that they come to and remain at a stop at some Lagrangian type points to bond molecules together defies credibility. Valence and bond theories unarguably work very well at macro levels, but the real underlying mechanism of bonding has been unknown until now. Macro in these terms means several levels above fundamental. At melting point, molecular motion increases due to photon absorption until motion amplitudes extend beyond the stable holding zone of Coulomb and L forces, which results in a phase change. Sufficient Coulomb and L forces remain for molecules to swap around and maintain some kind of random proximity in a liquid state, and this slide illustrates such a motion symbolically. In the pink we track a molecule through a whole lot of other molecules. There it's hanging on to a couple there, a couple there, a couple there, hanging on to a couple there, and bypassing the others. It's a little bit like a kid swinging along monkey bars. This slide, the total quantum of photons required to achieve this phase change is called the latent heat of melting. Further absorption of photons increase molecular activity until there's a total dissociation of forces and evaporation occurs at boiling point and we have a gas. Phase change is a relatively slow process, whereas an explosion is the opposite. In nuclei at approximately 10 to the minus 15 spacing, nucleons share their L's so that their combined L is less than the sum of the component L's. This L sharing and deficit is the reality behind what we commonly call bonding forces. In an explosion, molecules dissociate to a gas phase in something in the order of 10 to the minus 10 of a second, pretty quick. Now in explosions or any high energy exchange, or more correctly high momentum exchange, where L's and photons are forced together in a virtually zero time, the repulsive forces and resulting accelerations are extreme. And here, just symbolically, we have a couple of particles engaging together, molecules, electrons, whatever. The engagement time, 10 to the minus 15th of a second. The rebound distance, about 10 to the minus 17th of a metre. We can calculate an acceleration of 2 by 10 to the 13th metres per second squared, which is extreme and results in a copious emission of photons. This violent interactive activity becomes a chain reaction of all adjacent particles that occurs over a fraction of a second until expansion separates the particles enough so the interactive activity can't continue. Quite a spacing there. Such activity manifests itself as extreme temperatures, pressures and momentum of all the bits and pieces. Uncontrolled, it results in destruction. Controlled, it can do useful work. The excess of photons emitted during this exchange comes directly from an L deficit of the ingredients as they arrange to a lower energy state. An L deficit would be measured if this were possible in such an exchange, but it's not. The L deficit is replenished from the source, even during the explosive exchange, at any momentary constant velocity interval of the charged particles, as explained previously, i.e. they're not accelerating. In non-nuclear explosions, the L force overpowers all Coulomb forces at all times, so no transmutation of elements occurs. Nuclear transmutation, on the other hand, that's fission and fusion, requires extra inputs to stretch nucleon spacing and thus upset the L-Coulomb balance, inputs that are not present in non-nuclear exchanges. And there's reason to believe these inputs involve unattached neutrons, usually slow, neutrinos, the occasional electron, in addition to the inevitable cascade of photons resulting from these encounters. If you forgive my abbreviations, neutrinos, photons, nucleons, and we have a new element. And what can we do with this knowledge? We can create controlled ultra-high energy exchanges to occur over time intervals of days instead of microseconds we see in an explosion. And we can harvest a large portion of the energy and heat produced safely, cheaply and cleanly for the benefit of mankind and the environment. And how do we do this? We do this by oscillating electrons extremely fast in a controlled space, which means at an extremely high frequency. And if we look at this symbolic sketch, we have some electrons passing slowly between two charged plates of rapidly reversing polarity. The electrons oscillate, decelerating here, emitting photons, accelerate here, emitting photons, the same this side, up and down. If we do this very fast between the plates, we can emit photons and harvest the energy there. Whereas here, if we have the electrons travelling too fast, or the oscillating frequency between the plates too slow, we have no real acceleration, no photons produced. By this means, we're in a sense harvesting energy from controlled explosions. We're taking energy almost, but not quite directly from the source, instead of the multi-stage cycle that we are familiar with, and that is protein, oxygen, CO2, plus sunlight, rain comes down, trees grow, trees rot down into coal and oil and gas, and we finally burn the stuff to produce heat. That's a process that takes millions of years. Here, we do it almost instantly. And most importantly, because we involve no neutrons or transmutation of elements, it's a clean, non-nuclear process and produces no dirty residue as does fission and fusion. No massive accelerators are needed because we are teasing things apart using precise means instead of trying to bash them together. And hopefully we can retrofit existing coal thermal power stations. It's as simple as that. Let's do it.